Hello, my name is Jack Tarricone, and I'm a second-year PhD student at the University of Nevada, Reno with Dr. Ann Nolan. Today I'm going to be talking about my research project titled Quantifying Snowpack Metric Trends in the Sierra Nevada. The MODIS image displayed on this page shows the interannual variability in the snowpack in the Sierras. This project will hope to investigate to see if there's any trends in this interannual variability. This paper uses data published by Steve Margulis in 2016. The title of the publication is called A Landsat-Era Sierra Nevada Snow Reanalysis. Margulis and others utilize a fully Bayesian particle batch smoother to assimilate data back into a model. It only works retroactively, and it uses Landsat fractional snow-covered area, NLCD land cover, a downscaled land surface model, and Glenn Liston's 2004 snow depletion curve to give estimates of snow water equivalent at 90-meter resolution throughout the whole Sierra Nevada. In this research, we are going to be investigating trends for three different snowpack metrics. The first one is maximum snow water equivalent, which will be known as max SWE, and this is the maximum amount of snow water equivalent in a pixel that it reaches in a water year. The second one, snow cover frequency, which will be known as SCF, is the ratio of days that a pixel has over 5.1 millimeters of SWE versus the total numbers of days. The 5.1 millimeter threshold is set because that is the plus or minus of 0.2 inches, which is what a snow cell site is calibrated to. And the last and final metric is snow disappearance date, known as SDD, and this is the day of the water year at which a pixel has less than 5.1 millimeters of SWE in it. There are two main science questions we are going to be investigating in this work. First, and simply, are there any significant trends in the snowpack metrics we just defined in the Sierra Nevada? On the left here is a figure pulled from Manuela Girotto in 2014, doing a Mann-Kendall analysis in the Kern River Basin, with the blue representing a positive trend and the red representing a negative trend. And we hope to create maps that look similar to this. And second, is there a relationship between the significant trends and the physiographic characteristics of the landscape, such as elevation, slope, aspect, land cover, and latitude and longitude? The study domain shown below encompasses all land area in the Sierra Nevada above 1,500 meters, which is a total of 49,409 kilometers squared. This includes 20 main river basins on both east and west side of the mountain range that provide large amounts of water from their snowmelt to both California and Nevada. On the left side, we have a digital elevation model showing the higher elevation peaks in the southern Sierra and the lower elevation peaks as we get around Lake Tahoe. And on the right side of the map in B, we have a land cover type representation ranging from evergreen and deciduous forests to shrubs to grasslands to even bare earth at the higher, more alpine zones. The data Margulis et al. Produced is 32 years of snow water equivalent data at 90-meter resolution from 1985 to 2016. To visualize the analysis we're going to display the image on the bottom right. We're going to be taking a trend analysis of 32 years of annual data of each pixel, represented by the yellow there. If we think about it like the figure on the left here, latitude, longitude, and time, it's like a big data cube, and we're going to be analyzing each pixel in that data cube for significant trends. To complete this analysis, we created annual rasters for all three snow metrics for all 32 years of data. We then performed a Mann-Kendall non-parametric trend analysis on each pixel of these 32 rasters for each of the three metrics. And finally, we produced maps to display the significance and magnitude of the trends of all three metrics. Displayed below are the results for the snow cover frequency trend analysis. The full estimated trends are shown on the A side of the figure, while the B side displays only the significant trends, which have a p-value of less than 0.05. As we can see, there's a lot of trends that are centered around the area on the west shore of Lake Tahoe and a little bit north. As you go down and the elevation rises in the mountains, we see less density of trends. And then as you go south to the Kern River Basin, there's also a large density of significant negative trends here. So a negative snow cover frequency trend means that you are getting less snow cover on a yearly basis. Here are the results for snow disappearance date that are displayed below with the same format as the last slide above. These results actually follow a very similar spatial distribution as the snow cover frequency below. We have a density in the Kern River Basin. As we go north, the density lessens of trends. There's only scattered throughout this region, and then a very large density of significant negative trends, which means snow is disappearing earlier every year on the west and north shore of Lake Tahoe. And last, we have the results for SWE and the trend analysis that was performed. On first glance, we can see this map looks a little bit different than the last two we saw. The main difference is that on the west and north side of Lake Tahoe, the density of significant trends is much less. You still see a lot of negative trends in the southern part of the state at the Kern River Basin, and almost no trends of significance in the southern Sierra and the high peaks in there. This is just first pass of analysis. There's a lot more analysis to do on this project to sort of better understand why and how these trends are different and in what different areas they're in. Displayed on the map is the outlines of the Truckee and Carson River basins, overlaid with the maximum SWE data we'd looked at before. These rivers are mainly fed from snowmelt in the spring every year, and displayed on the map we can also see that there's a lot of red, which means there's a lot of negative trends in this area. This is the full trend analysis, not just the significant, but I think it shows the importance of understanding these trends for the future of water resources in northern Nevada and Lake Tahoe, is to understand how and when the snowpack is going to melt and when the water will be provided. And this sort of analysis sheds some light onto understanding what the future of Nevada water resources may look like. There's a lot of future work we plan to do to complete this research project. First, we're going to add 2 new snowpack metrics: the maximum SWE day of water year, and also a metric called MWA, or midwinter ablation events. This metric is tracking how much melt occurs, or how much loss in SWE, throughout the accumulation season of a snow year. We then will do a random forest analysis to classify the important physiographic variables for pixels with significant trends, to see if there's any sort of relationship between type of forest and a significant trend, elevation, slope, aspect. We're then going to compare all this to in situ snow pillow data, most likely SNOTEL, to validate all our results. And then finally, we're going to investigate at a basin scale, so look at each individual river basin and the volumetric SWE amounts, and relate that to discharge in the higher order mountain streams to see if this model is doing a good job at predicting the amount of water held in the snowpack and therefore the amount of discharge that will be in those streams. Just wanted to thank everyone for taking the time to listen to this presentation, and hoping you're having a great conference.